Hello class, welcome to STAT 1200. I'm your instructor William Buellman, and today we are covering section 6.1, the normal curve. Our objectives for today are use a probability density curve to describe a population, use a normal curve to describe a population, convert values from a normal distribution to z-scores, find areas under a normal curve, and find the value from a normal distribution corresponding to a given proportion. The following figure presents a relative frequency histogram for the particulate emissions of a sample of 65 vehicles. If we had information on the entire population containing millions of vehicles, then we could make the rectangles extremely narrow. The histogram would then look smooth and could be approximated by a curve. The curve used to describe the distribution of this variable is called the probability density curve of the random variable. The probability density curve tells us what proportion of the population falls within a given interval. The area under a probability density curve between any two values A and B has two interpretations. First, it represents the proportion of the populations whose values are between A and B, and it also represents the probability that a randomly selected value from the population will be in between A and B. The probability of success is the same in each trial. So in this curve up here, we see that shaded area is equal to the proportion of the population whose values are between 3 and 4. Alternatively, it represents the probability that a randomly selected value from the population will be between 3 and 4. The region above a single point has 0 width, thus no area. Therefore, if x is a continuous random variable, the probability that x equals a is equal to 0 for any number a. This means that the probability that a less than or equal to x is less than or equal to b is equal to the probability that a is less than or equal to x, which is less than or equal to b, for any numbers a and b. For any probability density curve, the area under the entire curve is 1. Because this area represents the entire population, and if you remember back to probability, if we have all the possible outcomes, they need to sum to 1, so the area under this curve has to be 1. Probability density curves come in many varieties, depending on the characteristics of the populations they represent. Many important statistical procedures can be carried out using only one type of probability density curve called a normal curve. A population that is represented by a normal curve is said to be normally distributed or to have a normal distribution. The population mean determines the location of the peak. The population standard deviation measures the spread of the population. Therefore, the normal curve is wide and flat when the population standard deviation is large, and tall and narrow when the population standard deviation is small. The mean and median of the normal distribution are both equal to the mode. So if we look at this left-hand graph, we can see that on the dash curve, when compared to the solid curve, the standard deviation is higher. It's 2 instead of 1, so it is more spread out and doesn't have as tall as a peak. Versus if we look at this right-hand graph, we can see the solid curve and the dash curve have the same standard deviation, so they have the same amount of spread and the same height, but since their means are different, it shifts the graph over because the mean is 5, so the peak needs to be over 5 instead of 0. The normal distribution follows the empirical rule. So the empirical rule, which we learned before, the normal distribution follows that empirical rule. Recall that the z-scores of a data value represent the number of standard deviations that the data value is above or below the mean. If x is a value from a normal distribution with mean mu and standard deviation sigma, we can convert x to a z-score by using a method known as standardization. The z-score of x is z equals x minus mu divided by sigma. For example, consider a woman whose height is 67 inches from a normal population, with a mean of 64 inches and a standard deviation of 3 inches. The z-score then would be z is equal to x minus mu over sigma, which is equal to 67 minus 64 over 3, which is equal to 1. So the z-score for this woman would be 1. So as we look at these two graphs, the top one is the standard normal curve, which has mean 0 and a standard deviation of 1. And this bottom one is our curve for the heights, which has a mean of 64 and a standard deviation of 3. And you can see how the points by this dashed line line up. So we have taken this curve that had a mean of 64 and a standard deviation of 3 and standardized it to the standard normal curve, which has mean 0 and standard deviation 1. A normal distribution can have any mean and any positive standard deviation. However, the normal distribution with a mean of 0 and a standard deviation of 1 is known as the standard normal distribution. Z-scores that have been converted from a normal distribution follow a standard normal distribution. Table A2 may be used to find the area to the left of a given z-score. So if we go to table A2 and we look at a z-score, let's go with 0.29. So we look here and we look here and we go where they cross right here. And now we have been given the area, or in this case the probability, that we are less than that value. Example 1. Find the area to the left of z equals 1.26, and you're going to sketch a normal curve, label the point z equals 1.26, and shade in the area to the left of it, and then consult table A2 to look up z equaling 1.26. Find the row containing 1.2 and the column containing 0.6. Here's our solution. So first we have to sketch the normal curve and label the point z equals 1.26 and shade the area to the left of it. So that's what we've done here. And to remind you, 0 is the peak, so 1.26 should be to the right of it, so that makes sense. So we're good there, and we're shading the area to the left, so that's why that blue is there. So now we have to consult the table. So we look at table A2 and we look for z equaling 1.26. We find the row that's 1.2, so that you can see over here is highlighted, 1.2 is highlighted. And then we match up the column 0.6, which is also highlighted, and find where that row and that column intersect, which is the value 0.8962. This tells us the area to the left of z equaling 1.26. So the area to the left of z equaling 1.26 is 0.8962. Example 2. A study reported that the length of pregnancy from conception to birth is approximately normally distributed with a mean of 272 days and a standard deviation of 9 days. What proportion of pregnancies last less than 259 days? First, we need to find the z-score, which z is equal to x minus mu over sigma, which in this case is equal to 259 minus 272 over 9, which equals negative 1.44. Now we have to find the row with negative 1.4, which is here, and the column with 0.04, which is here, and we find where the column and the row intersect, which gives us this value right here of 0.0749. So using table A.2, we find that the area to the left of z equaling negative 1.44 is 0.0749. So we conclude that the proportion of pregnancies that last less than 259 days is 0.0749. Or if we were to convert that to a percentage, we'd say about 7.49% of pregnancies last less than 259 days. Example 3. A study reported that the length of pregnancy from conception to birth, again, was 272 days for the mean and 9 days for the standard deviation. What proportion of pregnancies, in this case, we want to know, lasts longer than 280 days? Again, the first thing we need to do is find the z-score. So x minus mu over sigma, which is equal to 280 minus 272 over 9, which equals 0.89. So we need to find in table A2 the row that has 0.8, which is right here, and the column which has 0.9 or 0.09, which is right here, and then this box where they intersect gives us our area. So using table A2, we find that the area to the left of z equaling 0.89 would be 0.8133. The area to the right, therefore, is 1 minus that 0.8133, which equals 0.1867, because remember, the table gives us the area to the left, which would be less than 280 days, and we want to know more than 280 days, so that's why we have to do this 1 minus 0.8133. Thus, we conclude that the proportion of pregnancies that last longer than 280 days is 0.1867, or equivalently 18.67%. Example 4, same pregnancy data. So mu is 272, standard deviation is 9. But this time we want to know how many full-term pregnancies are there if we consider a full-term pregnancy between 252 and 298 days. First, we need to find z-scores as we've done before. So we're going to find the z-score for 252, which is x minus mu over sigma, which is equal to 252 minus 272 over 9, which gives us negative 2.22. And then the z-score for 298 is x minus mu again over sigma, which is equal to 298 minus 272 over 9, which gives us 2.89. So if we were to sketch the curve, here's our normal curve. So right here at the peak, we know the mean is 272. Then over here at like z equals 2.98, we have 298, which is z equals 2.89. Over here at 252, we know that z is equal to negative 2.22, and we care about this area in between. That's what we're trying to figure out. So using table A2, we can find that the area to the left of z equaling 2.89 is 0.9981. So that gives us everything to the left of 2.89, but that is too much area because we need to take out this area to the left of z equaling negative 2.22. So we need to figure that out. So the area to the left of z equaling negative 2.22 is 0.0132. Area between z equaling negative 2.22 and 2.89 is equal to the 2.89 area minus the area to the left of negative 2.22, which is equal to 0.9849. Thus, the proportion of pregnancies that are full term that last between 252 days and 298 days is 0.9849, or 98.49% of pregnancies last a full term. We may have been finding areas under the normal curve from given z-scores. Many problems require us to go in the reverse direction though. That is, if we are given the area, we need to find the z-score that corresponds to that area under the standard normal curve. Suppose we want to find the value from a normal distribution that has a given z-score. To do this, we solve the standardization formula, which was z equals x minus mu over sigma for x. The value of the x that corresponds to that is, so let's start with z equals x minus mu over sigma, and we're solving for x. So in order to do that, we multiply both sides by sigma, do some algebra, and we get z times sigma is equal to x minus mu. So now we have to add mu to both sides, and that gives us that x is equal to mu plus z times sigma. So that's our equation right there for x. X is equal to mu plus z times sigma. Example 5. Heights in a group of men are normally distributed with a mean mu of 69 inches and a standard deviation sigma of 3 inches. Find the height whose z-score is 0.6 and interpret the result. Here we have the formula. Remember, x is equal to mu plus z times sigma. We know mu, we know the z-score we want, and we know sigma, so we just plug it all in, which gives us 69 plus 0.6 times 3, that's mu, z, and sigma, which when we do that math, we get 70.8. We can interpret this by saying a man that is 70.8 inches tall has a height of 0.6 standard deviations above the mean. So remember, z-score is how many standard deviations above or below the mean you are. And since this is a positive z-score, it means we are above the mean. So this man who is 70.8 inches tall is 0.6 standard deviations above the mean. The following procedure can be used to find the value from a normal distribution that has a given proportion above or below it using table A2. So first, sketch a normal curve, label the mean, label the value for x that you want to find, and shade in and label the given area. If the area is on the right, subtract it from 1 to get the area on the left. Look in the body of table A2 to find the area closest to the given area. Find the z-score corresponding to that area. Obtain the value from the normal distribution. Example 6. Mensa is an organization whose membership is limited to people whose IQ is in the top 2% of the population. Assume that scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. What is the minimum score required to qualify for Mensa membership? Value X separates the upper 2% from the lower 98%. The area 0.02 is on the right, so we want to subtract 1 and work with the area of 0.98 on the left. The area closest to 0.98 in table A2 is 0.9798, which has a z-score of 2.05. The IQ score that separates the upper 2% from the lower 98% is X, which is equal to mu plus Z times sigma, which equals 100 plus that 2.05 we found times 15, which equals 130.75. Since IQ scores are generally whole numbers, we're going to round this value of X to 131. So what that is saying is in order to qualify for Mensa membership, you need to have an IQ score of 131 or greater.